Welcome back. This is the second of the two lectures on fault detection and classification, and the title names the method, Multivariate Statistical Process Control, which is usually written as MSPC. Unpack that phrase now, because everything today is an instance of it. Statistical process control means charting a measured quantity against the limits that come from the normal operation and raising an alarm when the run falls outside of them. Univariate means one chart per measured variable. Our trace has 2000 samples per run, so a univariate would mean 2000 charts, and those samples are heavily correlated. Multivariate means one model of the whole run and charting a small number of quantities derived from it. Today, there are two such quantities. T² measured how far a run sits from the center of a healthy population. SPE measures how much of the run the model could not account for at all. Each gets a limit, and the limit is measured from baseline rather than chosen. Lecture 1 built the model, a mean, run, 3 eigentraces, and alignment step. It ended with a detector that used a threshold I picked by hand, was scored on runs it was fitted on, and had no answers for a fault that keeps a normal shape. Today fixes all three and then asks a harder question of what such a system costs to run in a fab where the faults are rare. A short recap, because everything today rests on it. What we have: a baseline of 100 healthy runs, aligned so that the start time variation is gone, summarized by a mean run and 3 eigentraces. A compact code, 3 or 4 numbers, reproduce a healthy run to about 0.3% of its span. Then two detectors that no longer fire on runs we know are good. What we do not have is more interesting. We have no threshold with a reason behind it. A plus or minus 20 units used in the last lecture I picked by hand, and I said so at that time. We have no score for a new run. We looked at pictures and made judgments, and we have no evidence. Not one faulty run has been scored, so the detection rate is completely unknown. For all we know, both detectors are quiet because they are quiet about everything. The bottom row is the honest state of play. 100 training runs, 3 eigentraces, 0 fault stored, and 1 threshold chosen by hand. One more thing worth saying before we move on. Everything we do today is fitted on healthy runs and nothing else. That constraint is not a teaching simplification, and I want to keep saying it because it is easy to drift away from once label fault appear on screen in 10 minutes. Here is the standard pipeline for an fault detection and classification system, so you can see where we are. 6 steps. Segment, cut the raw log down to 1 recipe step, which you do using context data rather than the trace itself. Remove the start time variation. Model a baseline on known good runs. Detect, score each new run against the limit. Diagnose, attribute the alarm to parts of the run. Act, route it to an engineer. Lecture 1 was steps 2 and 3. Today is 4, 5, 6. One remark about 2 steps we are not covering. Segmentation and the action plan are engineering rather than modeling, and in my experience they are where most deployments actually fail. A beautiful detector attached to a badly segmented trace or wired to an alarm nobody reads does nothing. It is worth noticing what the pipeline does not contain. There is no step that learns what a fault looks like. Nowhere in the 6 boxes does a faulty example enter the model. The system knows what normal is, and everything else is defined by exclusion. That is what makes it deployable on a tool that has never failed in a way you have recorded. Let us try the obvious thing. Take the set point offset run from lecture 1. That is the run nobody in the room could pick out on slide 7, and the one holding the plateau about 10 units low. Align it, subtract the same mean run, project onto the same 3 eigenstates. No new machinery at all. We are using the model we already built on a run that it has never seen. On the left, the run in red against the baseline in gray. On the right, its coefficient plotted against the coefficients of the 100 healthy runs. It sits outside the cloud. Its first coefficient is minus 497, and the healthy runs have a spread of 88. That is about 5.5 standard deviations out. Recall from last lecture that after alignment, the first component tracks the plateau level. So, model is placing its run far from the others along precisely the axis that describes the quantity the fault moved. That is the system working. One thing to say aloud: this is the first time in 2 lectures we have used a label faulty run for anything. Notice how it's being used. The model is still built from healthy runs only. Label is being used to test the detector, not to fit it. Keep the distinction. We will need it again in 10 minutes. Look at the left panel for one moment before the scatter. The faulty run sits inside the gray band of the for the ramps, the overshoot and idle sections. It only separates on the plateau. That is exactly the picture from lecture 1, slide 7, except now we have a model that can turn the separation into arithmetic. Notice the axis on the right, the horizontal coefficient on E1, which after alignment means the plateau level. Vertical is E2, the idle level. The faulty run is displaced almost entirely horizontally. The model has put the displacement on the axis that corresponds to the physical thing that went wrong without anybody telling it which axis that was. Looking at a scatter plot works for one run in the lecture. It does not work for 20,000 runs a day. We need a rule that produces one number. The obvious candidate is distance from the center of the healthy crowd. Square each coefficient, add them up, take the square root, standard Euclidean distance. Try it and it fails immediately for the reason in the left panel. The three components are have wildly different spreads among the healthy runs: 88 units, 21 units, 11 units. They are not comparable quantities. Middle panel shows what that does. For this faulty run, the first component accounts for 99% of the plane square distance. The other two contribute 1% between them. A run that was perfectly ordinary on E1 and 5 standard deviation out on E3 would produce a small total and we would miss it. The fix is forced by the problem rather than chosen. Before you add the squares, divide each coefficient by the standard deviation that component has among the healthy runs. Now you are asking for each direction how unusual is this run in units of how much healthy runs normally vary in that direction. That is a comparable quantity, and the right panel shows the contribution rebalancing. It is worth being explicit about what the squared quantity means because it is a habit that transfers well beyond the lecture. After dividing by the standard deviation, each term answers the question, how many standard deviation from the typical is this run in this particular direction? 1, a value of 1 is ordinary, a value of 5 is not. Summing these squares, the squares of those is then a sensible total because you are adding comparable things. The expression has a name. It is hotel length T squared and it is about a century old. The formula is on this slide. Sum over components of T sub A squared divided by lambda sub A. Two symbols to be clear about. T sub A is the runs coefficient on component A. That is the number the projection hands you. Lambda sub A is the variance of that component among the training runs. That is the scaling we just derived. If you have seen T squared written down before and found the lambda mysterious, this is all it is. The amount healthy runs normally vary in that direction. The code is 6 lines and you have seen 5 of them already. Compute the mean, take the SVD, keep the first scale loadings, record the variance, project and sum the scale squares. What a large T squares means in words. A run is built out of familiar patterns in an amount the healthy population never produced. Every ingredient is one that the model knows. The recipe is unusual. The set point run scores 35. A practical note on the choice of K, the number of components you keep. Here it is 3 because lecture 1 showed that 3 or 4 reproduce a healthy run to about 0.3%. That choice matters for both statistics and it matters in opposite direction. Keep too few components and the real structure spills into the leftover, which inflates the second statistic on healthy runs. Keep too many and the model starts describing noise and the leftover shrinks towards nothing and its limit becomes unusually tight. The lab asks you to sweep K and see both effects. There is one more thing that is easy to miss. T squared is computed inside the space model spans. It says nothing whatsoever about anything outside the space. That is not a flaw, it is the definition and it is what the next 3 slides are about. 35 compared to what? We need a limit. The rule is the simplest one available and it is what industrial systems actually use. Score all the training runs. Sort the scores, put a limit at 99 percentile. Here that is 13.1. The left panel is the training scores on the log axis with the limit as a dashed line. The faulty run is in red are the far right. The right panel is the same scores as histogram, so you can see the limit sitting out in the tail. By construction, about one training in 100 sits above the limit. That is what choosing 99% means, and it is a false alarm rate you are buying. Choose 95 and you get 5. Choose 99.9, you catch fewer falls. It is a dial. There are textbook alternatives that put F distribution on F squared and the Jackson-Madhulkar approximation on the other statistic. Both assume the scores are multivariate normal. On 2000 point traces, the empirical percentile is simpler and makes fewer promises, so that is what we use. This slide also retires something. The plus minus 20 from lecture 1 is gone. The limit now comes from the data, and if you refeed the baseline after maintenance, the limit derives itself with no human in the loop. To sanity check, you should run whenever you see set a limit this way. First, look at where the limit falls relative to the bulk of training score. If it is sitting a long way out in a thin trail, then it is being determined by 1 or 2 runs, and it will move a lot if you refeed. Here it is set by a single highest of 100, so it is not robust to that one run. With a few hundred training runs, it settles down. Now let us try to break it. Same model, same limit, different fault. This is a glitch spike, a brief disturbance on the plateau about 40 units deep and a dozen ticks wide. An arc or an ESD event, physically obvious and definitely a scrap condition. Left panel, you can see it clearly in the trace. There is a notch around tick around 1400. Right panel, the coefficients, minus 56, minus 13, minus 11. Each one of them comfortably inside the healthy range. The point sits in the middle of the cloud. T squared comes out at 2.7 against a limit of 13.1. The run passes. So a fault you can see with your eyes, which would scrap the lot, is invisible to the detector you just built. Before fixing it, work out why it happened. Take the spike run, project it down to its 3 coefficient and then rebuild it. Multiply back and then add them. The left panel shows the original in red and the rebuilt in dark blue. The spike is gone. The rebuild is smooth right through it. The reason is structural. The model has 3 ingredients, the mean run and 3 eigentraces, which are all smooth, slowly varying shapes. Nothing in that set looks like 12 tick notch. The projection can only produce combination of what it holds, and so it produces the closest smooth thing, and the notch simply dropped on the floor. That is also why coefficient looked ordinary. The spike never reached them. It was discarded before the coefficients were computed. So the evidence we want is not the coefficients at all. It is what we got discarded. The middle panel shows the original minus the rebuild from the healthy run in teal and from the spike run in red. The healthy run leaves noise. The spike run leaves the spike and 40 units deep sitting there by itself. It is worth noting how general this is. The argument had nothing to do with spike specifically. It only used one property of the model, that it can reproduce combination of 3 fixed smooth shapes and nothing else. Any fault whose signature lie outside the span of those shapes will be discarded in the same way and leave the coefficient untouched. That tells you which faults to expect trouble with before you test any of them. Anything narrow in time, anything high frequency, anything with a shape that healthy population never produced. Conversely, faults that move a quantity the model already tracks will show up in the coefficients because those were exactly the directions the model spans. So the blind spot is predictable from the construction, which is a much better situation than recovering it empirically one fault at a time. So make that leftover into a number, square it, sum it over the whole run. That is the second statistic. It is called the square prediction error, written SPE, and in some text Q. The formula on the slide says exactly what we just did, x minus x hat square summed, and where x hat is the projection rebuilt. You have made this quantity already in lecture 1, slide 24, where the model is square pulse and got 7% error and a pure noise and 20 and got 23% against 0.3% for a real run. That gap was the whole point of the slide. This is the same measurement applied to a fault. Two more lines of code: center, project, construct, and take the difference, square, and sum. The limit is set the same way before the 99 percentile of training values. On the spike run, SPE comes out at 26,000, again a limit of 1,648. The second statistic catches it by a factor of 16. Now step back and see why there are two statistics, not one. The picture is the geometry. Your 2000 dimensional space is mostly empty. The healthy runs occupy a thin slab inside it, and the slab is the plane spanned by 3 eigentraces. Every healthy run sits close to it. A new run can leave the neighborhood in two independent ways. It can travel long way inside the plane. The shape is familiar, made of ingredients the model owns, but the amount is extreme. That is T², the golden arrow. Or it can sit out of the plane entirely. The run has a component the plane cannot produce at any coefficient values. That is SPE, the red arrow. They are orthogonal by construction, so they can carry independent information. A fault that is invisible to one is usually loud in the other, and that is why every production MSPC implementation monitors both. If you want a one sentence version, T² asks whether the run is in an unusual place, and SPE asks whether the run is a sort of thing the model can describe at all. A note on why the plane is so thin. There are 2000 dimensions available, and the healthy run use essentially 3 of them. That is not an accident of this data set. It is a consequence of the runs all being generated by the same recipe with a handful of parameters varying, and which is also true in a real tool. The physics constrains the data to a low dimensional set, and PCA finds it. That is the property the whole method rests on. A healthy run, if healthy runs fill the space uniformly, there would be no plane to be off and no compact code and no method. Whenever you meet a new monitoring problem, the first question worth asking is whether a healthy run is low dimensional in this sense, because if it is not, none of this applies. The slides answered the question you should be asking. SPE is computed on 2000 samples of the run. So why did we need the eigentraces at all? Why not just take the distance from the mean run and the threshold that? So let us just do exactly that and compare same 100 training runs, same 99 percentile rule, same held out wafer. The only difference is whether we subtract the projection before measuring. The left panel is the headline. Distance from the mean run catches 21 of 48 falls. SP catches 43. Adding T² brings it to 48. The reason is the limit printed inside each bar. Without the projection, the limit is 46,000. With it, 1,600, a factor of 28. Here is why. A perfectly healthy run does not sit on top of the mean run. It has its own gain, own offset, own drift. Those differences are real and they are large, and they set the limit. Because the limit has to sit above every healthy training run. Anything smaller than normal healthy variation is therefore invisible. What the projection does is remove that variation before measuring. X hat is the best model. X hat is the best the model can do with only the patterns healthy run exhibit. So X minus X hat contains only what those patterns cannot account for. The floor drops by a factor of 28, and faults that were sitting underneath is now into the view. The right panel shows it fault by fault. Glitch spike goes from 0.7 times the limit to 16. Access overshoot from 0.3 to 6.5. Noise bursts from 0.1 to 1.4. Notice the set point offset, which moves the other way from 4.1 down to 0.9. That is not a failure of the method. The plateau level is the direction the model owns, so the projection produces the offset and it disappears from the residual. That is precisely the gap T² fills, and it is why two statistics together reach 48. If you want one sentence for the exam, PCA is what makes the residual small for healthy runs, and small residual for the healthy run is what makes a small fault detectable. Let us check that claim across all 6 types from lecture 1. Each fault type is scored with both statistic. The bar shows the median score as a multiple of that statistic's own limit on a log scale, so anything to the right of the dashed line is caught. Set point offset. T squared 1.9, SP 0.9, caught by T squared alone. That makes sense. An offset moves plateau level, and the plateau level is the direction the model owns, so the run stays on the plane and just travels a long way across it. Glitch spike. T squared set point T squared 0.2, SPE 16, caught by SPE alone for the reason we spent 2 slides on. Slow ramp is an extreme case. T squared 4.4, SPE 600. The changed edge shape is far outside anything the model can build because eigentraces were learned from runs that all had the same edge shape. Plateau droop, excess overshoot, and noise burst all sit in the same pattern. Modest on T squared, clearly over the line on SPE. If you take one operational habit from this lecture, take this. When you see a paper or a vendor reporting a single anomaly score, ask which of these 2 things it is measuring and what it is therefore blind to. Now we need a number for how good this is, and that means label faults and a careful experiment. Both halves of the slide matters. On the left, how the faulty runs are made, 1 defect per run injected into a run that had already passed the hell gate. That second condition is important. If a faulty run were also an unusual healthy run, you could never separate the 2 effects in result. Severity is a knob, so each fault has a nominal magnitude that we can dial down later. 6 types, 8 runs each, 48 faulty runs in the total. On the right, how the runs are split. 100 healthy runs fit everything. The mean, the eigentraces, both limits. Those are exactly the 100 runs from lecture 1 unchanged. 40 more healthy runs come from the same generator with the same seed, so they are further runs of the same tool, and no model in this lecture is ever fitted on them. 48 faulty rounds come from the label population because that is the only place faults exist. The borderline is the one to hold on to. The model never sees a faulty run at any point in its construction. Why be this careful? If you fit on the runs you later score, the model has partly memorized them and you get a detection rate that no deployment will ever reproduce. This is the single most common way published anomaly detection results turn out to be optimistic, and it is easy to do by accident. One more design decision embedded in the split, which is easy to overlook. The 100 training runs and the 40 held out healthy runs come from the same population generated the same way. In the fab, they would not. Your baseline would be last month and your held out data would be this week with maintenance events in between. So this split measures how well the detector generalizes to the new run from the same condition, which is the easy version of the question. The harder question, generalizing across time, across chamber, is on the deployment side near the end. Here is the result. Every held out run scored on both statistics. The T squared across SPE up, both axes logarithmic. The dashed line are the 2 limits. Everything above or right of the dashed line is flat. Teal circles are the 48 held out healthy runs. Red crosses are 48 faulty runs. 48 of 48 false caught. 3 of 40 healthy runs flagged. Look at where the crosses sit. The cluster at the top right, high on both. A scattered group, high on SPE but low on T squared, sitting to the left of the vertical line. 32 of the 48 are caught by SPE alone. Take SPE away and you lose 2/3 of your detection. Now false alarms, because that numbers deserve attention. 3 of 40 is 7.5% and the 99th percentile promised 1%. The limit is too tight, and it is too tight for a reason we can measure directly. The model was fitted on those 100 runs, so the residuals on them are smaller than the residuals on runs it never seen. A limit defined from the training residuals before, therefore sits below what a new healthy run actually lands. Hold that thought. The slide on the baseline size measures exactly this and shows it shrinking as the baseline grows. I want to be careful about the perfect score. 48 of 48 is real and it is measured on this benchmark, which has one injected fall per run at the nominal severity, a well specified baseline. 3 slides from now we will start taking those conditions away. A couple of things to notice about the shape of the point cloud. The healthy runs form a tight blob near the bottom left, roughly 2 orders of magnitude below the falls on SPE. That separation is what makes the perfect score possible. It is not that the limits are clearly spaced, it is that the two populations barely overlap on this benchmark. The faults spread over 4 orders of magnitude vertically. The ones at the very top are slow ramps which change the edge shape and are therefore enormously far outside the model. The ones near the SPE limits are subtle plateau faults. And one honest observation, a few faults sit close to the limits. On the benchmark with slightly different severity or with a baseline collected under slightly different conditions, those would be the ones that flip. Perfect score has very little margin behind it, and the next 2 slides are about that margin. This slide answers a question the last few slides earned. An alarm is a number, so where in the run did it come from? Look at what SPE actually is. It is a sum. 2000 residuals, each one squared, added together into a single total. The act of adding is what destroyed the location information and nothing forces us to add. Panel 1 is the spike run in red with the models rebuilt of it in navy. Panel 2 is the subtraction R sub I equal X sub I minus X hat sub I, one number per tick. Panel 3 squares each of those numbers. SPE is what you get if you add up panel 3. The contribution plot is panel 3 itself. So there is no new computation here, no new model. The same quantity is being displayed at different levels of aggregation. In the same way, a monthly total and a daily ledger are the same data. On this run, 91% of the score comes from 25 ticks around tick 42. That is a sentence an engineer can act on. The next slide shows what the same plot looks like for faults that were spread out rather than concentrated. Detection is half of FDC. The other half is telling the engineer something they can act on. SP is a sum over ticks. If you keep the individual terms instead of collapsing them to a total, you get a plot against time and it tells you where in the run the model failed. 3 examples. Plateau droop, the contribution builds from the hold. Glitch spike, and the concentration is at the single tall line at tick 1442. Slow ramp, and it is concentrated at the edges. Why this matters more than the alarm itself? An alarm that says run 4471 is abnormal, closes no tickets. An alarm that says run 4471 is abnormal at plateau points the engineer at the heater. That is the C in FDC, and it is the difference between a systems engineer use and a system they mute. One caveat that will bite you if you skip it. These contributions are located in the aligned time frame because that is the frame the model works in. Before you report a tick number to a human, undo the shift so a number refers to an original recording. Before comparing detectors, be clear about what an ROC curve is, because it is easy to read as a mysterious object and it is not. Left panel, every run in the held out set already has one alarm score. The teal dots are the 40 healthy runs and the red scores are the 48 faulty ones, and the axis is the score on the log scale. The vertical dashed lines are 3 candidate thresholds. Nothing else is happening. This is the whole data set on one axis. Now take one threshold B at a score of 1. Count what is above it. All 48 faulty runs and 3 of the 40 healthy runs. That is the detection rate of 100% and a false alarm rate of 8%. Two numbers. Plot them as one dot, false alarms across, detections up. That is the point B marked on the right. Move the threshold and the pair of numbers moves with it. At A stricter threshold of 3, no healthy run is flagged, but only 62% of the false are caught. At C, a looser threshold, everything is caught, and a third of healthy runs alarm as well. Sweep the threshold across each value a score would take, and the dots trace out the curve. The area under that curve is a single number between 1/2 and 1. It is the probability that a randomly chosen faulty run scores above a randomly chosen healthy one. Its usefulness is that it compares detectors without either one having to pick a threshold first, which is exactly the comparison the next slide makes. Let us put these three detectors from these two lectures side by side on the same held out data. This is the ROC curve. For every possible threshold setting, it plots a fraction of false you catch against the fraction of healthy runs you falsely flag. Sliding the threshold moves you along the curve. The diagonal is what a random guessing gives you. The area under the curve summarizes the whole thing in one number, and 1.0 means every fault the run scored higher than every healthy run. No residual against the golden trace with no alignment. Area 0.74. Not much better than a coin. Same rule applies to aligned runs, 0.97. Aligned with T² and SPE together, 0.999. Notice the cost of each step. The first improvement from 0.68 to 0.98 cost 1 integer per run. No training, no tuning. The second improvement cost 3 eigentraces and 2 percentiles. Neither of those is a big model. Before we look at these two reality checks, fix the vocabulary because the rest of the lecture uses it. A new detector puts every run into one of the 4 boxes. A good run that passes, correct, and that is 99% of runs nobody should ever hear about. The good runs that get flagged, that is a false alarm, cheap ones. The slide after next is entirely about why it is not cheap in bulk. A faulty run that gets caught, correct, and the entire reason the system exists. A faulty run that passes, that is an escape. The wafers ship. This is the outcome the fab is paying to avoid. An important structural point is at the bottom. Moving the limit trades the second box against the fourth, and it cannot reduce both. Tighten the limit, you catch more faults and produce more false alarms. Loosen it, and the reverse. The detector is a choice about where on the trade you want to sit, and there is no setting that escapes it. 2 more pieces of vocabulary while we are here because you will meet them in papers. A fraction of faulty runs you catch is called recall, or a true positive rate or sensitivity depending on which field the author trained in. The fraction of alarms that turn out to be real is called precision. Those two are the pair that matters operationally, and the next slide is about the precision specifically because it is the one that depends on the fab rather than on the detector. The next slide sweeps something called severity, so define it first. Every fault type in this lecture has a nominal magnitude fixed when the fault library was written. A set point offset moves the plateau by 4.5%. A glitch spike is 20% of span dip. A slow ramp takes twice as long. Those are the values used on every slide up to this point. Severity is a multiplier on that magnitude and nothing else changes. The defect keeps the same shape, the same place in the run, only this size moves. Top row is a set point offset at 4 severities. At 25% of the plateau, at 25% the plateau sits 2.6 units off target, which is inside the spread of healthy population, and no honest detector would flag it. At 100%, it is 10.3 units, a value from earlier this lecture. At 2000%, it is 20.7 and completely separated. The bottom row does the same for a glitch spike from 20 units dip to 92. 2 things follow. First, asking whether a detector catches set point offsets is not a well-posed question until you say how large an offset. Second, at low enough severity, a fault is genuinely indistinguishable from a healthy variation, which is a property of the data and not the shortcoming of the method. That is what the next slide measures. For every fault type, how large a defect has to be before the detector reliably sees it. First, reality check. That perfect score was measured on nominal severity. So let us ask how large a fault has to be. Take each fault type, sweep its severity from 0 up to the nominal value used throughout these lectures, and remeasure the detection at the same limits. The horizontal axis is severity as the percent of nominal. The vertical axis is the detection rate. Read the ordering rather than individual curves. Edge faults are easy. A ramp 10% slower than nominal is already caught every time. The reason is the same one from lecture 1. The derivative is large at the edge, so a small change in the recipe produces a large change in the signal. Plateau faults are hard. Set point offsets and no bursts needs most of their nominal severity before detection becomes reliable, because the plateau is where signal the flat and the healthy population is tightest. So when someone quotes you a detection rate, the useful question is at what severity? A single number hides all of this, and the fault sizes that matter operationally are usually the small ones because the large ones already tripped some other limit. There is a practical way to use this curve that goes beyond reporting. Decide with a process engineer what magnitude of each fault actually matters. A set point offset of 0.5% might be within the spec and not worth an alarm. A 2% might scrap the lot. Then read off this plot whether your detector reaches acceptable detection at that magnitude. If it doesn't, know before deployment rather than after, and you know which fault type to work on. That conversation is much more productive than quoting a single detection rate, and also tends to reveal that different fault types have different cost, which the single number completely hides. Three definitions first, because the slide uses all three and only the first two have appeared so far. Detection rate is the faults that you caught divided by all the faulty runs there were. TP over TP plus Fn. False alarm rate is the healthy runs you flag divided by all the healthy runs. FP over FP plus Tn. Both are properties of the detector and both are what a benchmark reports. Precision is different. It is the alarms that turned out to be real divided by all the alarms you raised. TP over TP plus FP. Nothing in that formula is a property of the detector alone, because the number of false alarm depends on how many healthy runs went through and depends on the fact. Second, reality check now, and this is the one that decides whether the system survives. Detection rate and false alarm rate are properties of the detector. What an engineer actually experiences also depends on how rare faults are, and faults are very rare. Work the arithmetic. 20,000 monitored runs a day. 1% genuinely faulty, so 200 real faults. A detector at 95% detection and 5% false alarms, which sounds very respectable. Real alarms, 95% of 200, so about 190. False alarms, 5% of 19,800 good ones, so about 990. So the engineer sees roughly 5 wrong alarms for every one that is right. The quantity that matters here is precision, the fraction of alarms that are real, and it is about 16%. What happens next is predictable. Engineers mute the alarm inside a month, and then the system catches nothing at all. The detector that switched off has a detection rate of 0 regardless of what its ROC curve is saying. The curve on the left shows how steeply precision depends on the fault rate. At 1%, you need a false alarm rate well under 1% before the alarm is worth reading. There are only 3 levers here, and it is worth knowing which is which. You can lower the false alarm rate, which means tightening the limit, which costs you detection of smaller errors. You cannot raise the false rate, which you cannot do and would not want to. Or you can reduce the number of runs each alarm represents by grouping alarms per lot or per chamber per shift instead of per run, which is what real systems do, and which is an interface decision rather than a modeling one. Notice that improving the model helps only through the first lever. A better detector moves you along the same trade-off curve. It does not remove the arithmetic. That is why this slide sits in this lecture about method. Third practical matter, and this is the debt from lecture 1 slide 10 where I said 100 runs is a realistic baseline and left it there. Fit the same model on 10, 20, 40 and 100 healthy runs. Then score 40 healthy runs that none of those models ever saw. Left panel shows two curves. The gold one is the SPE limit for each model sets for itself. The gold one is the SPE limit. Remember where a limit comes from. It is the 99th percentile of the training scores of that particular model. So each of these four models produces its own limit from its own 10, 20, 40 and 100 runs. Nothing is carried over between them. The TL curve is the median SPE of the 40 held out healthy runs, which are the same 40 runs every time. With 10 training runs, the limit sits far below where unseen healthy runs actually land. The right panel is the consequence. With 10 training runs, every one of the 40 held out healthy runs break the limit. With 20, a third of them. With 40, a fifth. With 100, 7.5%, which is the same 3 runs out of the 40 you saw on the result slide. That connection is the point of this slide. False alarms on the earlier slide were not bad luck. They were the finite sample effect, and this curve shows the size of it. The mechanism is worth stating in general terms because it is not specific to this method. A model with k-free direction fitted on n samples will always fit its own samples better than it fits new data, and the gap shrinks as n grows. With 10 runs and 3 components, the model can bend to accommodate its training set almost exactly, so the residuals it sees during the fitting are unrealistically small. So the limit derived from them is unrealistically tight. The practical rule for MSPC is a baseline of at least a few dozen runs and preferably a couple of hundred. Note that even at 100%, we have not reached 1% of the percentile promises. So if you need the false alarm rate to be what it says on the tin, you either collect more baseline runs or you set the limit on a held out set rather than on the training set. If someone hands you a detector fitted on 10 runs, this is a failure mode to check first. The previous slide ended with a claim, so here is the measurement behind it. The problem is that the same 100 runs did two jobs. They fitted the mean and the eigenstate, and then their own score set the limit. A model bent to fit those exact runs reproduced them unusually well, so their residuals are unusually small, so a percentile taken from them lands too low. The repair is to give the two jobs to two different runs. Fit on the part of the baseline, then score the runs you deliberately held back and run the fits never saw and take the 99th percentile of those scores as the limit. Those residuals are the size an unseen healthy run really reproduces. The experiment holds a total number of healthy runs fixed because that is the real constraint in a fab. Gray means all of them were used for fitting and the limit came from the same runs. Teal means 70% were used for fitting and the limit came from the other 30%. With 20 runs in total, the false alarm rate falls from 36% to 20. With 60, it falls from 10% to 2.5, which is finally close to that 299 percentile promise. With 100, both came down to a 7.5%, so there is nothing left to recover. The right panel is the cost. A smaller fit set is a slightly worse model, so detection dips by a point or two. One caution about vocabulary. These held back runs are not a test set. They are part of building the model. They are all healthy, and 40 runs used to report performance are separate from both. If you calibrate the limit on the same runs you later quote a false alarm rate from, you are back to reporting a number no deployment will reproduce. We have been building something with a name, so before replacing it against the alternative, let us say plainly what it is. Start with the middle two words. Statistical process control is an old and simple idea. Measure something on every run and decide from the normal operation what range that measurement occupies. Draw the range as a limit on the chart and alarm when the run falls outside. Sure charts in the 1920s, and the same logic is running in every fab today. The only open question is which quantity you chart. The obvious answer is chart the measurement itself. It is univariate SPC, one chart per variable. The left half of this slide shows three charts, the sensor value at tick 400, at tick 900, at tick 1400 across the same run. A trace that has 2000 samples, so being thorough means 2000 of this. Two things go wrong with that. First, multiplicity. 2000 charts at 3 sigma, each will flag something on almost every run for no reason at all. On our data, the rule alarm is if any sample is out of range, flags 28% of healthy runs and still catches only 80% of the false. Second, independent. Those 2000 samples are not independent quantities. They are one physical run, and the lecture one showed that 3 numbers reproduce it. Charting them separately throws away everything the correlation tells you. Multivariate means one model for the whole run built from that correlation and then charts on quantities derived from the model rather than on the raw samples. That is the right half. 2 charts, both with a limit, and every one of the 12 faulty runs sit above one of them. Now map the vocabulary onto what we actually built. The mean and the eigentraces are the model for normal operation. T² and SPE are the charted quantities. The 99th percentile are the control limits. The contribution plot is the diagnosis step. Nothing in the lecture is outside the SPC tradition, and the whole contribution is the choice of what to chart. Now let us put this method in context, because everything we have done is a 1990s technique and you were in an AI course. 4 tiers. Univariate statistical process control. Extract features from the trace, plateau, mean, rise time, overshoot, settling time, and put each one on its own chart. A Shewhart chart plots the value itself. An EWMA chart, which is an exponentially weighted moving average, plots and running average that leans on recent runs. A Kuhn chart, a cumulative sum, accumulates departure from a target, so a small persistent shift eventually shows. Interpretable and almost no data required, and it catches drift across runs very well. Blind to anything the summary statistic does not capture. Multivariate SPC or MSPC, which is today. A principal component analysis baseline scored with T² and squared prediction error plus contribution plots. It handles the whole trace rather than a few features, and it extends to many channels. It assumes one operating mode and a linear subspace. Kernel and nonlinear PCA. The same construction carried out in feature space or a mixture of local linear models. These buys you curved and multimode baselines at the cost of interpretability and tuning. Learn encoder. Autoencoder sequence model self-supervised pre-training on unlabeled runs. These scale to many correlated channels with nonlinear coupling, and they need volume compute and monitoring of their own. Each tier buys something the tier above cannot do and gives something up. There is no tier that dominates. Here is the connection between the tier we did today and the tier at the bottom, and it is closer than it looks. A linear autoencoder trained to minimize squared reconstruction error provably recovers the principal subspace. This is a theorem, not an analogy. So everything we built this hour was an autoencoder written in linear algebra. Follow the mapping. The encoder is the projection onto the eigentraces. T equals P transports times x minus the mean. The code is the vector of coefficients, 3 numbers. The decoder is the reconstruction. X hat equals the mean plus P times T. And the reconstruction loss, the thing the autoencoder is trained to minimize, is exactly the quantity we call SPE. So when you read a paper on deep anomaly detection for time series, you are usually reading about the same construction with a nonlinear encoder and a nonlinear decoder substituted for the 2 matrix multiplication. That carries over unchanged in the part is the part around it. You still fit on healthy data only. You still set a control limit for the training reconstruction errors. You still decompose the reconstruction error over time to produce a contribution plot. The scoring logic, the limit, the diagnosis all survive the substitution. This is a useful thing to know because it means the habits from today transfer. So when is the nonlinear version worth it? The useful question is which problem you have rather than which method is better, where a learned encoder genuinely wins. Many correlated channels, dozens of sensors with nonlinear coupling between them, where the hand-built features stop scaling and a linear subspace is a poor fit. Large unlabeled archives because millions of healthy runs is precisely the setting self-supervised methods are designed for. When multiple operating modes, several recipes running on one tool where a single plane does not describe the healthy population. What it costs. You now have a second system to monitor because the encoder itself shifts and needs a retraining policy that somebody owns. Diagnosis gets harder since contribution plots exist for nonlinear models but are less direct than decomposing a sum of squares. And the honest one, which applies to every comparison you will read and write. Weak baseline, flatter, deep models. If a paper compares a deep autoencoder against a raw unaligned traces, it is measuring the value of alignment, not the value of the network. Compare against aligned MSPC before claiming an improvement. Finally, the things that break deployed systems. None of these are modeling problems and all of them will land on whoever builds one. Post-maintenance drift. After preventive maintenance, a pool legitimately changes. Seals get replaced, the chamber gets clean, and every trace shifts. Your baseline is now wrong. Somebody has to decide when to re-baseline. Both errors hurt. Re-baseline too early and you fold a genuine fault into your definition of normal. Too slowly and the system alarms continuously for a week until people stop reading it. Chamber mismatch. Nominally identical chambers are not identical. One baseline per chamber is usually necessary and it multiplies the number of models you maintain, which is an operations problem rather than a modeling one. Recipe changes. A recipe edit invalidates baseline immediately and the recipe edits are routine. Alarm fatigue, which we did the arithmetic for. A muted system detects nothing. I put this slide near the end deliberately. The modeling part of FDC is a dozen lines. The part that determines whether it is still running in a year is everything on this slide. 5 things to take away. 1. 2 ways to be abnormal. 2 statistic. T² catches a familiar ingredient in an unusual amount. SPE catches a shape the healthy population never produced. On our 6 fault types, setpoint offset is caught by T² alone and glitch spike by SPE alone, so monitoring one of them costs you a third of your detection. 2. The limit comes from the training scores, the 99th percentile of the fitted runs. That retires the handpicked threshold from lecture 1 and it rederives itself whenever the baseline is refitted, which matters because the baseline gets refitted after every maintenance event. 3. Fit on good runs and get the sample size right. With 10 training runs, the SP limit is too tight and every held out healthy run alarms. With 100, it is down to 7.5% and it is still falling. 4. A perfect detection rate needs context. 48 of 48 caught with 3 of 40 falsely flagged is a real measurement on its benchmark at nominal severity, which with a clear baseline. The severity floor and the base rate arithmetic are 2 things that decide whether it survives contact with a fab. First, the AI version is the same construction. Encode, decode, and monitor the decoder could not rebuild. A nonlinear encoder changes the first 2 steps and leaves the third one alone, which is why the habits from these 2 lectures transfer directly. The lab. The notebook generates every figure in both decks with fixed seats so you can arrange one thing at a time and see what moves. 3 pairs. Generate the healthy population and reproduce both lecture 1 failures, which should take you very little code. Implement landmark alignment and remeasure so you see the numbers change under your own hands. Then the open part. Fit the MSPC baseline yourself, sweep the number of components K and the limit percentile and report the severity fault for each fault type. That last part is where you will find out how much the answer depends on choices I made quietly. 2 caveats I want on the record. Traces are simulated. The magnitudes are realistic and the failure modes are real ones, but there is one injected fault per run, no drift, no mode changes. The real achieve is messier in all 3 respects, and the under the curve of 0.999 is a property of that benchmark rather than of MSPC. It is exactly why severity floor slide and the base rate slide exist, why I would not put that number in a report without both of them beside it. Public databases if you want something real for a project. CCOM, the Tennessee Eastman process, and the semi-PCB and WM811K wafer map seats if you want the classification half of FDC rather than detection half.